In this video, we continue with chapter 5.5, and we are going to see how to find the cross product of two vectors in R3. So in R3, we define the cross product of vectors u, which has got components u1, u2, u3, or we could write it as u1i, u2j plus u3k, so u1i plus u2j plus u3k. And then vector v with components v1, v2, v3, or that we can write as a linear combination of the basis vectors, similarly as v1i plus v2j plus v3k. So we define the cross product here as u2 v3 minus u3 v2 multiplied by I. And so this is kind of like what we saw when we did the cofactor expansion. So for I, the components that it gets multiplied by is the determinant of these other four elements or components that are not in the same column or row as I. So essentially you can think about this as the cofactor expansion. And then u cross v, the second component is u3 v1 minus u1 v3. So if you want to visualize that, here's j, and we're taking the components that are not in the same row or column as j and doing the determinant there. And then for k, we take the determinant calculation of the u1, u2, v1, v2, which gives us this u1, v2 minus u2, v1 multiplied by k. So you saw this same calculation when we did our cofactor expansion. And then the right side is a determinant, essentially containing vectors I, j, and k. So the cross product is undefined for vectors and vector spaces other than R3. So this is only in R3 that we have this calculation. And so here are some of the algebraic properties of the cross product. So the first one is that u cross v equals negative v cross u. And then the second property is that u cross v plus w equals u cross v plus u cross w. The third property is that if you have a scalar c multiplied by u cross v, that's the same as the scalar c multiplied by u cross with v, or you could do u cross with the scalar c times v. So that scalar can get multiplied by either u or v when you distribute. And then u cross 0 is the same as 0 cross u is 0. And then u cross u is 0. And then u dotted with v cross w is equal to u cross v dotted with w. And all of that is just this determinant with u in the first row, v in the second row, and w in the third row. So for the proof of this, you can see our textbook. They have all the steps written out there. And then theorem 5.18 is some geometric properties of the cross product. So we're going to assume u, v, and w are non-zero vectors in R3. Then u cross v is orthogonal to both u and v. So what that looks like, I'll do my best to draw. Here's u, here's v, and then u cross v is orthogonal in R3. So it's orthogonal to the plane where u and v meet. The angle theta between u and v is given by the norm of u cross v, which is the norm of u multiplied by the norm of v multiplied by sine theta. And so we saw similar properties with dot product. U and v are parallel if and only if their cross product is 0. The parallelogram having u and v as adjacent sides has an area of the norm of u cross v. And then the parallelepiped having u, v, and w as edges has a volume of u dot v cross w. So let's take a look at some examples of these properties in action. So in our first example, we're going to find the area of the parallelogram with vertices here at 5, 2, 0, 3, negative 6, 7, 7, negative 2, 8, and 5, negative 10, 15. So the solution is going to be the area of, the area is going to equal the norm of u cross v. So u cross v is going to be this determinant here. ijk in the first row, and then the values here are the values in the rows are the adjacent sides. So remember, the parallelogram has what we're going to call u and v as adjacent sides. So u here is -2, -8, and 7. So you could try to draw out this parallelogram in R3. I'm not very good at drawing at R3, so you're gonna have to take my word for it to visualize that these are the parallel sides, or adjacent sides, I'm sorry. And then the other adjacent side is 2, -4, and 8. And so we get the determinant, which works out to be -36 plus 30j plus 24k. That -36 should have an I on it. And so then the norm of this is going to be -36 squared plus 30 squared plus 24 squared, all added together and square rooted. So that works out to be 6 multiplied by the square root of 77, or about 52.6498. And then our next example is to find a vector orthogonal to u equals -4, 3, -4, and v equals 4, 7, and 1. So here we do the cross product to find the orthogonal vector. So u cross v has u in the first row and v in the second row, and then, sorry, u in the second row and v in the third row, ijk in the first row. And then we do the determinant to get our vector here, 31i minus 12j minus 40k. And remember, ij and k are just our basis vectors. So here I is just 1, 0, 0. So if you want to write out the standard basis vectors instead of writing ijk, that's fine. If you've done physics class, you're probably in the habit of writing ijk, so whichever you prefer. Okay, so this week we'll do some group work to practice some of these applications.